Next we move on to pin jointed structures, and a pin jointed structure is very simply defined as being one that has all the connections between the various members, such as in this example you can see lots of different members, but the critical issue is at every junction you have effectively a pin which allows all the various members connecting at that point to freely rotate around that point. In so doing, you can't transfer bending to any of the members, and that is the beauty and the simplicity of a pin jointed structure, in that none of the members can experience bending. They can only experience axial force, either tension or compression. I'd strongly recommend you go and have a look at this link here. There are lots of others similar to it, but this one is particularly good at explaining the concept I've just talked about moments ago. Now you can't click on it here, but you can click on it in the notes that I provide you. There's a link that you can click on to go straight to that little video. So in each of these members, as we said, there's either going to be tension or compression. Now we've already touched on it in previous sections, but the way we are going to show that on the drawing is via arrowheads towards each other in the case of tension.
It's 18 hours.
And in the case of compression, if this red member happens to be in compression, we're going to put arrowheads away from each other. Now that is significant when we get to analyze the forces, because it immediately shows us the effect of the green member on the junction would be a pull from right to left, as you can see by that arrowhead. And also at a glance we can immediately see, when we see arrowheads facing each other, it immediately tells us that there is tension in this member. A useful way of remembering the little rhyme, we call it the T rhyme. T stands for tight, tension, towards. Okay, so let's just go through those words. They all start with T. If a tension member is in the place of this green member here, it simply means we could effectively replace it with a piece of string or a rope or a cable, which are all items that can only resist tension. They obviously can't have any compression in them. So you could visualize it as a tight member, a tight piece of string. If you were to take your fingernail and flick it like a guitar string, you could sense that it was tight. It's called tension. That also starts with a T. And then finally, towards tells us that the arrowheads are always drawn towards each other, like this. So that is how the sign convention works, and it's very useful to us when we get to calculate. Conversely, compression is drawn that way, with arrowheads away from each other. Now there are various ways of calculating the magnitude of the forces in the members. In our section of work we're going to use primarily the method of sections. Okay, and the way that works is you make an imaginary cut across the framework, and then you consider the equilibrium of the cut-off section of the truss. And typically you would take the side that is easier to analyze, the one where you have more known forces. But whenever you make the cut, you are allowed to take left of the cut or right of the cut. Whichever one you choose to use, that's fine, but you must then consider the full equilibrium of that cut-off piece. And at the outset, we have to make assumptions about whether the members are in tension or compression. And what we normally do is we just assume, if we certainly don't know, we assume that they're in tension, and we proceed with the calculation, and if the numbers come out negative, we then make the deduction that they are in fact the other way around, in other words, compression. Now we talk about the conditions for equilibrium. If an object is still, in other words, it is in static equilibrium, the sum of all the forces acting in any direction on a point must add up to 0. What that means in simple terms is forces acting up on a point are equal to forces acting down on a point. Forces acting to the left are equal to forces acting to the right. Forces in any other direction, for example 45 degrees or some other arbitrary angle, forces in the one direction must equal forces in the other direction. And then secondly, the sum of all moments of the forces about any point must also add up to 0. Let's remember what a moment is. A moment of a force about any point is the product of the force and the perpendicular distance from that point to the line of action of the force. Okay, for example, the moment of force P about point A is the force magnitude multiplied by this perpendicular distance AB. So in simple terms, whenever you want to know the moment of a force about any point, you simply extend the line of action of that force right across your page. So take your ruler, and in this case we have force P over here, so we take our ruler and we align it with force P, and we just extend the line right across your page with a faint construction line. Then you sit back and you say, right, where's the moment's point? In this case it's A. And you ask yourself the question, what is the shortest distance from point A to a point on that line? And that's going to occur at a point perpendicular to A. It doesn't quite look like it in this drawing, but that is supposed to be 90 degrees over there. So at a point along this line, where you are perpendicular to the moment's point, that will give you the shortest distance. And that is your moment arm. You simply take the magnitude of the force and you multiply it by that little distance AB, and you will get the moment of the force P about A. The units of moment are Newton meters, product of force and distance. If we have a number of moments, it's often useful to set up a sign convention. And clockwise moments are normally made to be positive, and anti-clockwise moments are made to be negative. And then either we can say clockwise moments all added up equal anti-clockwise moments all added up. Or if you wish, you can simply sum all the moments and equate them to 0 if you have used the sign convention correctly. It'll come to the same thing. So when you are taking moments of a force about a point, you can do it the way we've just described moments ago, which is going to be loosely referred to from here on as method A. But there is another way of doing it, which sometimes might be quicker and easier for you. But let's just start by recapping on method A, which is essentially the same as this up here. Let's look at the moment of the 100 Newton force about point A. Once again, extend the line of action across your page. Find the shortest distance to the moment's point, which would be a perpendicular line to the line of action. Determine that by graphical means or by calculation. In this case, we've used calculation and found that distance x is in fact 1.732 meters. And then you simply multiply the magnitude of the force, which is 100 newtons in this case, by that distance, 1.732 meters, and get an answer, 173.2 Newton meters. Now we get to method B, as we call it, and that is going to achieve exactly the same result, but we are going to replace the 100 Newton force with two components. Now remember, that's perfectly okay to do. You can either stick with just the original force and deal with it as in method A, or you can replace the 100 Newton force, throw it away, and replace it with two other forces that have exactly the same effect as it. Those would be known as components. And then you look at the moments of those two forces, also about point A. But here's the magic. 100 cos 60, which is one of the components, we'll discuss in a moment how we get the components, but this particular component happens to run exactly through point A. And that is when you have no moment at all. When your force has a line of action that passes through the moment's point, there is effectively zero distance between the line of action and the moment's point. So no matter how big the magnitude of this component is, it can have no turning effect or moment about point A. So it's going to be 0. And then you are left with the only other one remaining, which is 100 sine 60. And it is simply multiplied by the full 2 meters, because after all, that is the perpendicular distance between its line of action and point A. And you'll see that when you multiply 100 sine 60 by 2, you're going to get a 173.2, which is the same as before. Now you must watch closely how we got to the 100 cos 60 and the 100 sine 60 as components of the 100 Newton force. Now there are various ways you could do that, but here is the quick way that I like to use. So what I do is I take the 100 Newton force and I can either leave it where it is, or I can take it and I can place it on this side. Remember, a push force on the one side can be replaced as a pull force on the other side of the point. Exactly the same effect is attained. So we have 100 newtons over there. Now the angle was given as 120 degrees over here, which means that because this is a straight line, if we have 120 degrees here, we must have 60 degrees there. Remember, they must add up to 180. So if we have 60 degrees over here, we can then simply in our minds take the 100 Newton force and rotate it about the point in question through an angle. Now what's that angle going to be to get down to this horizontal? Well, it's going to be 60 degrees. There's the 60 degrees. And this is what you remember. If you take the original force, 100 newtons, and you rotate it through a given angle, 60 degrees in this case, you will reach the cos component. And that cos component is going to simply be original force, cos, always cos, the angle that you rotated through. And then once it's done, you do it first, always do the cos one first. By process of elimination, the other component, which is perpendicular to it, will be exactly the same 100, exactly the same angle, but there will be a sign over here. So to recap, let me ask you a question. What is the horizontal component of the given 2,400 Newton force? Well, as I explained, you take the given force and you rotate it in your mind through the given angle. So here it's lying, and in your mind you see 20 degrees and you simply rotate it clockwise to let it lie down here. This is all in your mind. You visualize it. And you say to yourself, right, the 2,400 Newton force, I had to rotate through 20 degrees to get to my desired angle. That will then be the cos component, as we call it. So that would be 2,400 cos 20. By process of elimination, the other one, so let's just finish by drawing in that arrow. It would lie like that. And the other component perpendicular to it would be, by process of elimination, the same 2,400, the same 20 degree angle, but in here goes sine. So the vertical component would be 2,400 sine 20. Right, another example. What is the horizontal component of the given 120 Newton force? Stop the video and give it a try. What is the horizontal component of the 120 Newton force? Right, first of all, we are wanting horizontal component, that is in this direction. There will also be a vertical component. Now, first of all, is it possible to get a vertically up component from this force? The answer is no. This force is downwards to the left, so in vertical terms it can only have a downward effect, and in horizontal terms it can only have a left effect. There's no ways that this 120 Newton force, the way it's orientated, could have an effect on this point that made it rise vertically up. So that's not going to happen. And it could also not have an effect on this point to make it move to the right. So that's also not possible. So before we even carry on, we know that the horizontal component is going to be something magnitude left. And the vertical component is going to be something magnitude, but it's going to be down. Right, now let's remember the little rhyme. We always start with the cos component. And that's the one we obtain by rotating in our minds the original force through the given angle. The given angle was 60 degrees. So in our minds we take this force here and we rotate it about this point where the green dot is, and we would have to rotate it by 60 degrees to get to the vertical. Now that was not what was asked for, but you have to do that first. And that is always going to yield 120 cos 60. Why is that? Well, it's original force, 120, cos, because that's the first one we always do, and 60 is the angle that we always rotate through first. Then, by process of elimination, the other one, which we've already decided by inspection must be to the left, is going to be original force, 120, not cos, sine this time, and it's still the very same force, 60. So to finish off, 120 cos 60 works out to 60 newtons, and in brackets we can put in down to show that we fully understand not only the magnitude of the vertical component, but also the direction. Similarly, the horizontal component, 103.92 newtons, turns out to be left, so we put that in. So the 120 Newton force can safely be replaced by two components, one vertically down of magnitude 60 and one horizontal left of magnitude 103.92. And that's what you need to know to be able to continue with the method of sections and resolving moments. So just to go back to this one to reinforce how it was worked out one last time, the 100 Newton force started as a push, and I replaced it as a pull on the other side, which is absolutely legal. We're allowed to do that. And then for convenience, I decided to replace that green 100 Newton force with two components in useful directions. Useful in this case being the one aligned with a line that passes through the moments point, thereby getting rid of it in a moment, and the other one nice and perpendicular to our 2 meter long member. So we have the first one being 100 cos 60, because we know that this angle is 60, so we take the 100 Newton force, rotate it in our minds through the 60 degrees and get the 100 cos 60. It's ultimately going to fall away because it's multiplied by zero distance, so you won't see it in this equation at all. On the other hand, the 100 sine 60 is multiplied by the full 2 meters, and you get to find exactly the same outcome as before, 173.2 Newton meters. Okay, here's a useful little video you might want to watch, which explains moments in case you're not completely familiar with that concept. So go to the notes and click on that link there. Now remember what the purpose of this whole section is. It's to work out the internal forces in the various members of a framed structure like this, or a pin-jointed structure, let's call it. But sometimes before you can dive into the inside of the structure and start analyzing it, you need to know external forces. And either they're all given, or in this case, this example over here, there are some external forces that need to be resolved. So that is a separate matter to the method of sections where we get into the internal members. We are still talking about external forces, and in this case we've got to find the magnitude of L and R, which are both unknown to us at this point. So globally, this whole structure, which you can see is made up of a number of different members, is in equilibrium, and because of the fact that it's standing still, we can deduce that it's in equilibrium, and it is in equilibrium under the influence of all the external forces, of which there are 1, 2, 3 that are fully known and 2 that are unknown. Now the conditions for equilibrium are identical whether we are looking at the global structure as one big part, or if we are inside the structure working with a method of sections. It boils down to the fact that the sum of forces in any direction must be 0, and the sum of all moments adds up to 0 as well. So we're going to apply that to the structure over here. So often we use a little checklist, the 4-point checklist we call it, and that simply is point number 1, vertical forces add up to 0, ups equal downs in other words. Point number 2 is lefts equal rights. Point number 3, forces in any other direction add up to 0 as well. So if there were forces in, say, this direction, we would say forces that way are equal to forces that way. That's point number 3. Point number 4 is moments about any point also adds up to 0. In simple terms, clockwise effects about any particular point are equal to anti-clockwise effects about that very same point. So that is a 4-point checklist that we can go through when we get stuck. In our case, for this particular example, summing vertical forces is not going to help us because we have two unknowns in the vertical direction. Horizontal direction is not going to help us at all because the unknowns have no horizontal influence at all. Other directions, not of use to us. So we have to go to point number 4, which is to consider the moments. Now, we can take moments about any point we desire when we are solving for moments. However, there are often clever places to take moments about. And in the case of a situation where we have two unknown forces, L and R are both unknown, here's the trick. If you take moments about point D, which is the spot where L passes through, you will effectively eliminate L out of the one moments equation. And then later, if you take moments about point A, you will eliminate force R out of another moments equation, thereby having only a single unknown in each calculation. And that is the trick that you've got to remember. So with that in mind, we start off by summing the moments about point D. And to do that, you place your finger on point D, and then you hunt for all the clockwise moments that you can find. So my finger is on D, I'm keeping it there, and I start by hunting for clockwise effects. The only clockwise effect I can see is force 18, whose line of action is over here, is pressing on this whole framed structure from left to right at a point higher than where my finger is, which is trying to make the structure turn clockwise. So that is a clockwise moment. 18 multiplied by the distance of 3 meters. Remember, line of action of the force, what's the shortest distance to the moment's point? 3 meters. So this here is a clockwise moment. And if you look through the structure, you won't find any others. So then we can have an equal sign. And on this side of the equation, we look for anti-clockwise effects. Let's see if we can find where the 2 times 10 is. Well, here we have 10 kilonewtons pressing down on the structure. And remember, your finger is over here. That's the moment's point. So 10 newtons pressing down on the structure to the left of where my finger is, which is our moment's point, would cause anti-clockwise rotation. Force times distance, and that's on the anti-clockwise side of the equal sign. There's another one as well. R is upwards, and it is to the right of where my finger is. So that is trying to make the whole frame turn anti-clockwise. So it belongs on the left-hand side with all the anti-clockwise moments. So what we have is clockwise moments, 18 times 3, are equal to anti-clockwise moments, which are those two over there. And the only unknown is the magnitude of force R, and that turns out to be 4.25 kilonewtons. So we know that here you must have a force upwards of 4.25 kilonewtons for this entire frame to stay where it is in perfect equilibrium. Now we still need to find the magnitude of L, so we do a very similar thing, and we take moments about the other clever spot that we discussed earlier, which would be A, which is going to eliminate R. Now I know we know R, but for safety's sake, if we'd made a small error over there, we don't want to use R unnecessarily because it could have an error in it. So let's start again from scratch with a clean sheet of paper basically, and take moments about A, thereby eliminating R, and finding the clockwise moments and the anti-clockwise moments. And once again, 10 times 10 meters to my finger, 4 plus 4 is 8, plus 2 is 10. You put your finger on A and you leave it there, and you find that 10 kilonewtons times 10 meters is which type of moment? Do you decide? Anti-clockwise moment. 10 kilonewtons times 10 meters. 10 times 10 is an anti-clockwise moment, and there are no others that I can find, so that leaves us with an equal sign, and then the clockwise moments. And we have L times 8 meters, L times 8 meters, back to my finger, plus 18, here it is up here. Extend the line of action, find the shortest distance to the moment's point, it is 3. So 18 times 3 is another clockwise moment. Clockwise turning effect about the point where my finger is. So here are the clockwise moments, and they are equal to the anti-clockwise moments, and from it we can solve for magnitude of L at 5.75 kilonewtons. So far we haven't even started with the method of sections. We've just shown you how to use the principle of equilibrium to find external unknown forces on a structure. Let's start off with a real-life example of this very simple device, which is used on the back of a tractor for lifting loads. So we are going to be particularly interested in this little structure over here, which consists of a beam and a strut and members over there. Here you see it in two different positions, and the way it works is it connects to the back of the tractor onto the 3-point linkage. On the back of most agricultural tractors you have a 3-point linkage. These two arms can rise and fall with hydraulics, and you have a linkage over here which connects to the implement, and you're able to raise and lower the implement that you're working with, and that's exactly how this one works. So the question says the mobile crane shown below is to lift 750 kilograms. Well, you saw the image of the crane moments ago. When the jib is horizontal, what will be the magnitude of the force in the chain, magnitude and direction of the reaction at the hinge at E? So let's have a look at that. When it's horizontal, we've got to answer those two questions. What is the magnitude of the force in this chain between A and C? That is this chain. There it is. There the jib is more or less horizontal, and that is AC. So we've got to find what's going on in there. And I think you would agree that just by looking at it, there will definitely be tension in that chain. First of all, a chain can't have anything other than tension in it. You can't push something with a chain. You can't have compression in a chain. And even looking at it logically, there's a pivot over there. This is going to be tight. So that little rhyme about T, tight tension towards, is going to apply to that member over there. We've also got to find the magnitude and direction of the reaction at the hinge at E. So that is over here. Remember, there's a hinge pin. You can see there's a pin going through there. It pivots. So we've got to find what force is happening at that point over there. And then lastly, we must find the magnitude of the force in the member BD, which is this member over here. We've got to find the magnitude of the force in that member. Here was the layout. Remember the 85 degrees and these dimensions that are given, and also the fact that the 750 kilogram mass is hanging from another chain. You can see it over there on the end of the truss. So here is the truss redrawn, and we've figured out that in this member over here, because we are supporting 750 kilograms and there's only one cable, or in this case chain, supporting the 750 kilograms, the magnitude of force in the chain will be 750, the mass, times 9.81, because we're on Earth, and that's going to give us 7357.5 newtons of force in this chain. And also, looking at it, it has to be tension, and tension has arrowheads facing each other, towards each other. So T, tight tension towards, applies to that member. On this side, we have a chain that is inclined, remember, 5 degrees from the vertical, because we had 85 degrees over there. So if we take the original force, the green force, and we rotate it through 5 degrees, we will reach the cos component. So therefore we have original force, cos angle turn through, FAC cos 5 is the downward component, the vertical component which is downwards of the green force. Its partner is FAC sine 5, which would be left, because the green force can only have leftward effect and downward effect on point A. So we're going to throw away the green force and replace it with FAC sine 5 left and FAC cos 5 downwards. Now let's consider for a moment what's going on over here. At this point there is a pin that passes through 2 plates and allows this whole contraption to pivot around that point. Now there's most definitely some sort of force going on at that point, transferring or supporting this truss at that point. In fact, it's going to be a shearing action on that pin. If you were to pull the pin out and stick your finger in the hole, definitely that wouldn't be a good thing to try, because there's going to be massive force over there acting on your finger. But the point is, there is something going on there, and we've got to go and analyze the magnitude of the force at that point. It's one of the things we've been asked. So the way we do that is we put in the force immediately as 2 components in useful directions. In this case, vertical and horizontal are useful to us because other forces are in vertical and horizontal directions. So in vertical terms, let's think about what effect we must apply to the whole truss to keep it where it is. Well, if we're pulling down on the left, pulling down on the right, it follows that to keep this thing where it is, we're going to have to push upwards here in the middle. So our vertical component, we're going to immediately assume that it is upwards, and we're going to call it reaction at E, bracket V for vertical. So it represents just one component of the real picture, the full force at E. Then in horizontal terms, it must have some sort of horizontal component, because there is also an effect over here which is pushing the member from right to left. So for equilibrium in horizontal terms, we're going to have to give a little nudge to the right to counter that one. So we put that in as reaction at E, brackets H for horizontal. And if we can resolve each of those, we can then find the total force at E. But we'll do that later. Let's start by solving for the very first thing asked, which was the force in chain AC, which is this one over here. Right, so we've got our normal equilibrium conditions that we can look at, which was forces up equal forces down, forces left equal forces right, etc., and even moments we can look at. In other words, that 4-point checklist that I spoke of a little while ago. So checklist point number 1, let's see vertical forces. How many unknowns do we have? Well, it looks like we have 1 here and 1 here, which makes 2. So that's not going to help. Horizontal forces, we've got an unknown and an unknown. As soon as we have 2 unknowns, we're stuck. But how about moments? If we take moments about a clever spot, we might be able to eliminate some of the unknowns, thereby making the problem solvable. And the reason for choosing point E for starters is we want to find force AC. So it would not have been smart to start by taking moments about A, because we would have lost the very force that we want to find, because it would pass through the moments point and it would not be in the picture at all, because it would be times 0. So let's pick another spot. If we pick this spot here, we will eliminate this unknown and this unknown, because they've passed through the moments point. And that's going to leave us with a situation where we can actually solve, because we only have 1 unknown. So I'd like you to place your finger on E and start looking for clockwise moments. So my finger's on E and I'm looking for clockwise effects on this whole contraption over here. And I can immediately see FAC cos 5 multiplied by this distance, which is 0.5 meter, is a clockwise moment. Because if my finger's here and I pull downwards, I'm tending to make the whole structure turn clockwise. That is why it is a clockwise moment. Force times moment arm, or distance. There are no others that I can see. My finger's still on E. Now I look for anti-clockwise moments. And immediately I see 7357 pulling down. Look at the arrow closest to B, multiplied by the 1.5 meters back to my finger. And there are no other anti-clockwise moments that I can find, which means I can solve for FAC, which is a force, and I find it at 22.1568 kilonewtons. And that would be the full force, remember the one that's inclined at a slight angle of 5 degrees to the vertical. That is the full force in chain AC. Now we can go back to the checklist and take point number 2, which is sum of horizontal forces, adds up to 0. In other words, forces left equal forces right. And we only have 2. REH is a force to the right, and it must be equal to FAC sine 5, which is a force to the left. And therefore we can find the magnitude of that force. Then checklist point number 1 says ups equal downs, or the sum of vertical adds up to 0, whichever way you want to see it. But I'll just simply look at it as ups equal downs. We have an up and we have 2 downs acting on the whole structure. And they are FAC cos 5 is a down, 7357.5 is a down, and it's equal to the up. The only up is REV, which is over here, which is what we would like to work out, and that comes out to 29.43 kilonewtons. So at this point, what we know about point E is that there is a vertical component, REV, which is known to us, and there is a horizontal component, REH. But we would like to know what the single force is that has those two components. Okay, and to do that we use Pythagoras, and we draw a little triangle and we say, right, if we have upward effect and rightward effect of those two magnitudes, what is the total effect? Now the total effect would be a line joining the starting point to the ending point of those two vectors drawn head to tail. So draw your two little vectors head to tail, and that simply means that the tail of the second one is connected to the head of the first one, and then you get the total, the resultant force, by joining the starting point to the ending point. So in simple terms, RE using Pythagoras would be the square root of the first, the vertical, squared, plus the horizontal squared. This you've done before, and you find that the total value of RE is 29.49 kilonewtons, and you can even work out the inclination of that by taking tan theta. I'll take theta as this little angle here, which is this side of the triangle over that side of the triangle. So this force RE of magnitude 29.49 kilonewtons is inclined at 86.25 degrees to the horizontal as shown. So far all we've solved is point A and point B. We haven't started on the method of sections yet, and that's what we're now going to do in part C, where we've got to find the magnitude of the force in member BD. Now BD is an internal member of this pin-jointed structure. Okay, here it is here. To find that magnitude, we are now done with external forces. We've got all of them. We now dive into the truss itself and we analyze an internal member. And to do that, we use the method of sections and we make an imaginary cut through the truss in a place that cuts the member whose magnitude, whose force magnitude you wish to know. Now we need to know BD, so it's logical that we're going to have to cut through the truss there where the little red dot is moving. So we're going to cut through there, and we're then going to analyze one side, either the left of the cut or the right of the cut, whichever one is convenient for us. And we're going to analyze it for full equilibrium, because after all, it is standing still. So therefore the conditions of equilibrium apply. The 4-point checklist, ups equal downs, lefts equal rights, forces in other planes add up to 0, and ultimately moments. About any point add up to 0, or clockwise moments equal anti-clockwise moments. So all of that we're going to have to apply to find force magnitude BD. So this is what we're going to be doing. We're going to cut through the structure at that point, and we're going to focus on this remaining piece here. That is our piece of interest. This is the piece that we're going to consider the equilibrium of. Now here where we've cut through, we are going to consider what's going on at this point, and the easiest way to consider that is to pretend that you have a piece of string continuing out of the structure along where the original member was, and go to the next node point, which is outside of the structure. That's fine. But if we were to keep this object still and there was a force pulling down over here, what we would have to do in this direction is pull tight and attach to this point over here. What that boils down to is we're going to have to apply a force in this direction to keep this structure still and where it is. So the green force is going to have to be applied to the structure, and we can see it, as I said, as a piece of string that is connected all the way down here, and the string is actually tied off over there. Okay, now it's convenient to break that force, that green force, into components, and we already know well how to do that. We're going to swing the green force through the known angle, which turns out to be 11.3 degrees. If you look at tan phi at 0.3 over 1.5, so we can get this little angle at 11.3 degrees. So if we take the green force and we swing it clockwise 11.3 degrees, we get to the horizontal, and that will be the cos component. So there it is, FBD cos 11.3 is the horizontal force that we've got to apply to the end of the string to keep this whole thing in equilibrium. And we're doing it up here at this next point D. At the same time, remember, when you replace a force with components, they always come in pairs. So the other one is FBD sine 11.3, which would have to be upwards on the green dot to keep our structure where it is in equilibrium. And we'd have to do a similar thing down here, but the question actually only asks for FBD, so perhaps we won't even have to work that out. But let's proceed and consider the equilibrium of the cutoff section. And to do that, we're going to take moments about a point that is going to eliminate the unwanted unknowns. Now that is FBE, because it wasn't asked for, as I recall. So let's take a point that will make it fall away. That's why we're not even going to have to work it out. So that's why E is a clever point, because the unknown, unwanted force BE passes through it, so it's going to fall away. So we're going to take moments about E, put your finger on E, and start looking for clockwise moments. Right, finger is on E, clockwise moments. I'm seeing FBD cos 11.3 from left to right, and it is some distance from my finger, which is at E. That distance is 0.3 meters. So FBD cos 11.3 times 0.3 is a clockwise effect about E. There are no other clockwise effects that I can see, so I'll put an equal sign down, and then I'll start hunting for anti-clockwise effects. And I can see 7357 acting downwards 1.5 meters from my finger, which would be an anti-clockwise effect. So from all of that, we can solve for the magnitude of BD at 37.515 kilonewtons, which is the internal force in member BD. So 37.5 kilonewtons of tension in that member over there when you are supporting 750 kilograms. Right, example 2. We have a loaded truss shown down here. Determine using the method of sections the magnitude and nature of the force in the member joining points E and C. So here's E, here's C, so we need to know what's going on in this member over here. Take note of this little statement. make the cut between double arrowheads, apply the arrowhead that is applicable to the isolated portion. Remember that, we're going to come back to that in a moment. So there's our structure, and we are going to make the section, this imaginary section, such that we pass through the member that we need the magnitude, the force magnitude of. So it will be as per the red section there. And I'm going to choose to isolate the right hand side and consider this portion and throw away this portion, because to me that's simpler. But first things first, we can't do any of that until we find what these support reactions L and R are. And to do that, we've done that a few times already now, we look at the total equilibrium of the entire structure without making any sections. And I'm going to take moments about A, and that's one of the clever spots because it's going to eliminate one of the unknowns. Remember, L passes through A, so it won't feature in the moments equation. And our clockwise moments are equal to our anti-clockwise moments. And the clockwise moments, if my finger's on A, are 2000 times 2.5, 2000 times 2.5, and 3000 times 7.5. Remember, extend the line of action across your page, find the shortest distance to the moments point. And those are the two clockwise moments, and the only anti-clockwise moment is R times 10. Unknown force R times the full 10 meters. And from that you can solve for R's magnitude at 2750 newtons. Now move your finger to D and take moments about D. It's the other clever point because it eliminates unknown force R. And once again you hunt for clockwise moments. L times 10 is the only one I can see. L times 10 meters. It's equal to the anti-clockwise moments, 2000 times 7.5 meters plus 3000 times 2.5 meters, allowing us to solve for L at 2250 newtons. At this point you might wish to check your answer and check, are ups equal to downs on this entire structure? Well, it looks like it, because L plus R would be 2250 plus 2750. Check that it adds up to 2000 plus 3000, being the only two down forces, and yes it does. So it looks like these two calculations were indeed correct. So we're going to consider the equilibrium of the portion of the truss to the right of the imaginary cut, in other words this piece over here. So let's think what's keeping it there. First, external forces, 2750 up, 3000 down. Then if we look what's going on in these members, now by inspection it would appear as if this must be compression. If I press upwards here and upwards here, I think most of you would agree that that looks like a compression member. So I can safely put it in as compression arrowheads. If however you are unsure, you can make it tension, and then if it yields a negative number you can reverse it later. But if you can figure out that it is definitely compression, then put it in as compression. At the bottom here, I think you would agree if I press up here and up here, this member would be under tension. It would be tight. It would be tending to stretch this member. But if you can't see it, as I said moments ago, put it in as tension and we'll sort it out later when we get our answer. But here I've put it in as tension, arrowheads towards each other. This one here, I have no way of knowing whether it's tension or compression, so I will assume it to be tension and sort it out later. My section cut line passes between the double arrowheads. Now we must go back and remember this statement over here. Make the cut between the double arrowheads, we've done that. Apply the arrowhead that is applicable to the isolated portion. Apply the arrowhead, that's from the two, you've got to choose which one to use. You must use the one that is applicable to the isolated portion. Now I must consider the equilibrium of this portion over here. And let's see how many forces are keeping this isolated portion where it is. Well, we have 1, 2, 3, 4, 5 forces keeping it where it is. Now 3 of those 5 are unknown. So we're a little bit stuck unless we find a clever point to take moments about. And there's only one spot I can see that's going to eliminate two unknowns. And that is the point where these two lines intersect. Because if we take moments about that spot, we are going to eliminate one unknown and another unknown and allow us to solve for the only other unknown, which is BC. So it means we're going to have to first find BC and then only find EC, which was the force that we actually want to find. But it looks like we have to go a little bit on a roundabout route and do it this way. First of all, can you take moments about a point that is outside of your piece that you're analyzing? And the answer is definitely yes. We are analyzing this portion over here, and we can take moments about a point within it or outside of it. So E is fine. We're allowed to take moments about E. And E is a smart point because it's going to eliminate those two unknowns because they pass through point E. So put your finger on E and start looking for clockwise moments, thereafter anti-clockwise moments. So finger on E and let's look at clockwise moments. I'm seeing 3,000 multiplied by the distance back to point E, which is 2.5 meters. Because that's 5, so halfway between the two would be 2.5 meters. Remember, this is a 60, 60, 60 triangle, so it is nice and symmetrical. So that's 2.5 meters. The other clockwise moment is FBC. There it is there. Its effect on our isolated portion is from left to right. Look at the little arrowhead. Times 4.33 meters. Where did that come from? A little side calculation over there told us that the height from here down to there was 4.33 meters. That was our second clockwise moment. There are no others, so an equal sign. And then 2750 times 5. That is 2750, which is R, times the 5 meters back to where your finger is at E. That allows us to find FBC at 1443.4 newtons. It came out positive, indicating that our assumed nature of the force BC as being compression was indeed correct. Now we're in a position to find the force that we actually want, which is force EC. And to do that, we already now have force BC. We must find a place to take moments to eliminate one unknown, the one that we don't know and don't need to know, and that is ED. So where can we take moments to eliminate ED? Well, it doesn't help taking moments about E. We've already done that. So if we look at the line of action of ED, it passes through point D. So if we take moments about D, we are going to eliminate this unknown unwanted force over here, but we are going to retain this wanted force EC in our equation, and we can use the force BC that we've just found. So moments about D, fingers on D, clockwise moments, 1443.418, which is the force we just found, BC, multiplied by 4.33. Okay, BC times 4.33. Force BC times 4.33, a clockwise moment. There it is, clockwise moment about the point. There are no other clockwise moments, so it's time for an equal sign. Then we have anti-clockwise moments. 3,000 times 2.5. We discussed where 2.5 came from a moment ago. And then comes the one that we want to deal with now, which is FEC cos 60. That is the component of EC that is horizontal, multiplied by the full 4.33 height. And FEC sine 60, which is vertical, multiplied by the 2.5 meters. Right, where did those two components come from? Well, FEC is 60 degrees to the horizontal. So if you swing EC through 60 degrees, you will get to the horizontal, and that is where you find the cos component, remember? So FEC cos 60 is the horizontal component of force FEC. By process of elimination, the other component, which is vertical, would be FEC sine 60. Same angle, but now with sine. And that is where those two come from. And that's going to allow you to find the magnitude of force EC, but note it comes out as a negative number, which tells us that our assumed nature of EC as being tensile is incorrect. It is in fact compression. So all you need to do is write there that force EC is 288.68 newtons with a compressive nature, and that solves that problem. Right, next up is example 3. Determine the magnitude and nature of the forces in members DE and BE of the loaded pin-jointed truss shown below. So now would be an excellent time to stop the video and make an attempt at all of that before restarting the video and looking at the solution. As usual, before we can get into the truss and make the cut and look at internal forces, we've got to look at the overall external forces, keeping the whole frame in equilibrium, and L and R are missing for starters. So we take moments about clever spot A to eliminate L and allow us to find R. Clockwise moments, anti-clockwise moment, there's R. Similarly, take moments about C to eliminate R and have clockwise moments, L times 8, and anti-clockwise moments, those two there, allowing you to find L. To check, that plus that must equal that plus that, ups equal downs. Right, now we're ready to start. There's our cut. This is the piece that I'm leaving behind that I'm going to analyze for equilibrium. 1, 2, 3, 4, 5 forces, keeping it where it is. Problem, because 3 are unknown, so we must find a clever spot to eliminate at least 2 of the 3 unknowns. The only spot that's going to allow us to do that right from the get-go is the point where those two intersect, thereby getting rid of those two. That point is point D. Good place to start with your first lot of moments. Finger on D. Clockwise moments equal anti-clockwise moments. My finger is on D, and I have a clockwise moment of 40,000 times 3. 40,000 times 3 meters, half of 6. Plus another clockwise moment, FBE times 3. Where does that one come from? FBE, there it is there, times 3. I could have broken BE into components, but I spotted that there is a perpendicular distance I can quickly work out of 3 meters. From here to here is 3 meters. Figured out on this little side calculation over here. So I can simply put it as FBE times 3 meters as a clockwise moment. And it's equal to the only anti-clockwise moment acting on this isolated piece, which is 37500 times 6 meters back to D. And that's going to allow us to get the value of force FBE, which is not what was asked for. We've got to find something else. Actually, we were asked for BE, but we were also asked for DE. So now we can carry on and work out DE by taking moments about the other clever spot, which is C, which is going to eliminate this unknown and that force as well. So finger on C, and we find minus 40,000 times 3 minus FDE cos 60 times 6, all adding up to 0. Now you'll see I'm just doing this slightly differently to normal. Normally I say clockwise moments equal anti-clockwise moments, and I make everything positive. But you can of course use this method, which is to sum moments about C as 0 using the sign convention. So notice the negative and the negative indicating anti-clockwise. So it's your choice whether to do it this way or using sign convention and adding up to 0. It comes to the same thing. Anyway, from all of this you can find that FDE is negative 40,000 newtons, which means that it is a strut compressive. Remember, we assumed it to be the other way around as a tension member. The negative sign now tells us that it's in fact a strut. In other words, it's in compression. Next up is this structure. And in it we've got to find the forces in members AB, AD, BC and BD of the pin jointed structure. Now we're going to need a few dimensions that are not available on this sketch over here for when we start taking our moments. So it's convenient to drop a vertical and make a new point E over here. And then you'll see I've used the sine rule to find the distance from A to B. And then I've considered triangle ABE. And I've said sine 45 equals BE over that known size there. And I've found the distance from B to E, which I'm going to need shortly. And I also found that the distance from A to E was 0.3661 meters. I'm sure there's other ways of doing this, but that is how I did it. So we'll refer to those sizes in a moment. Next up is to make an appropriate cut through the structure, to cut through members that we want magnitudes for. So there's my first cut, and I'm going to consider the equilibrium of the left portion, this piece down here. And to do that, I'm going to take moments about D initially, which is going to eliminate this unknown force over here and allow me to find the other one, in other words AB. So I'm going to take moments about D, and I'm going to start by taking clockwise moments, FAB cos 45, which is the horizontal component of the AB force, times 0.3659 meters. We worked that out a moment ago. That is a clockwise moment. Then there's another clockwise moment, which is the other component of AB, which is FAB sine 45, multiplied by, extend the line of action, find the shortest distance to the moment, 0.6339 meters. And that's all equal to the only anti-clockwise moment, which is 1,000 times the distance back to D, which is a meter. It was cut off there, it's 1 meter. So AB is 1414.49 newtons, and the assumed direction of tie, which is the word used for a tension member, is correct, so we leave it as it is. Now if we take moments about another point, we can find the other member that we've cut through, AD. So if I take moments about B, I will now put this into the equation, and what I've got to do is I've got to put my finger on B, and I've got to look for clockwise moments. My finger's on B. Clockwise moments would be AD, which is pushing our isolated portion from right to left, multiplied by this distance, 0.3659, which we worked out up here. So that's a clockwise moment, and it's equal to the only other moment, which is an anti-clockwise moment, of 1,000 times 0.3661, which is the distance from there to there. And there are no other forces or moments involved here because they pass through the moments point B. So that allows us to find FAD at 1,000.546 newtons. So that cut found us 2 of the 4 forces that we need to find. But clearly it's not allowing us to find the others. We'll have to make another cut, and that's why this second cut has been made. And once again, I'm going to consider the equilibrium of the left portion, this piece over here, which is held in equilibrium by 1, 2, 3, 4, 5 forces. And once again, I'm going to take moments about a spot to eliminate 2 unknowns if I can, because we have 5 forces, 3 unknowns. And if I can eliminate 2 unknowns and get down to 1 unknown, I can solve it. And the spot that's going to eliminate 2 unknowns is D, because this one and this one both pass through D, so that's a very good place to start. So sum of moments about D, clockwise moments equal anti-clockwise moments, finger on D, and here we go, FBC cos 30, which is the horizontal component of BC, taken up to the next point, namely C. Its moment arm about D is 0.732 meters, it's clockwise. and that's equal to the anti-clockwise moment of 1,000, there it is there, times 1, the full meter back to D, plus, let's not forget, 1,500 newtons times the distance from its line of action back to D, the perpendicular distance, at 0.6339 meters, allowing us to find force in BC at 3077.38 newtons. Now there's only one force to go. So now there's only really one point remaining that we can take moments about, and that's point C, which is going to put these two back into the equation and remove this one. So finger on C, and we have 1,000.546 multiplied by 0.732, which is AD down here times 0.732. 0.732 being the distance between D and C. There it was over there. Okay, and that's equal to FBD cos 30 multiplied by 0.732 as well. There it is there, multiplied by 0.732. Remember, we're taking moments about C. And then we also have 1,000 times 1. There's the 1,000 times the full 1 meter back to there. And of course the 1,500 times the 0.6339 meters back to here, because that's the perpendicular distance through C. So BD comes out at minus 1922. So the assumed direction is incorrect. In fact, BD must be a strut. In other words, it must be in compression. Right, next we have a railway bridge. Here's a picture of it. And it's supported at its ends. So at A and at B, it's supported. It's resting on rock over there and rock over here. And it's two identical parallel trusses next to each other, this one and the one that you see in the background. And then to test its strength, they are applying point loads here and here, 250 kilonewtons and 200 kilonewtons. Treat all joints as pin joints and calculate the magnitude and nature of the forces in members HD, DF and FE. Okay, so once again, good time to stop the video and make a good attempt at that before pressing play once again to see the solution. Right, HD, DF and FE are over here, so it makes sense to make one cut right through all three. Let's see if we can do it in one shot like that. Okay, a little side calculation for distances. D to E was worked out using tan of 60. You can have a look at that. Next up is to work out the support reactions, L and R. We've done that a number of times, so that is not part of the method of sections. That's just looking at the equilibrium of the whole bridge. And we take moments about A to find R, and we take moments about B to find L. And then we do a little check to see that ups equal downs. Please have a look at that. Now we dive into the method of sections properly. There's our cut, and I'm going to analyze the equilibrium of the right hand portion, to everything to the right of the cut. Once again, 1, 2, 3, 4, 5 forces keeping that portion where it is. And you've picked up the trend by now, I'm sure. 3 unknowns. Clever spot is the one that eliminates 2 of the 3 unknowns, which would be this one, because both that force and that force pass through it, thereby eliminating them and thereby taking you down to 1 unknown, which is just that one there. So finger on F, take moments about F, clockwise moments equal anti-clockwise moments. There they are, 2 clockwise moments, 1 anti-clockwise moment, HD you've got. And as exactly the same as the others, you then take moments about another spot, which is going to then bring these two back into the equation to allow you to calculate them, and you then find DF at 105.854 kilonewtons. And finally, to find the last remaining one, you take moments about the only other logical spot, which is D, clockwise moments, Fe times 2.598. Fe times 2.598 is equal to 291.67 times 1.5, which is R times the 1.5 meters back to D. There's D, so that is 1.5 meters, which allows you to find force Fe at 168.4 kilonewtons. And here's a particularly simple one to finish off with. It's a pin-jointed frame, is used as a crane, so we pull down on this side, it's pivoted here, and we lift a load on the left-hand side. A little bit like that very first one we did. So a load of 1 metric ton, which is 1,000 kilograms, is lifted. Neglect the mass of the structure itself and calculate the required tension T. So how hard must we pull down here to balance the load on the other side? And then we must find the support reaction at the hinge. And finally, we must find the force in member AD, which will involve a cut. So stop the video as usual and work that out before looking at the solution. Moments about B would allow you to have the clockwise moment of T times 1 equal to the anti-clockwise moment caused by the load of 1,000 times 9.81 times the 2 meters to B. And it will allow you to solve for A at 19,620 newtons. So that's very simple. Now the force at B, in other words the support reaction at the hinge, can only be vertical because there are no horizontal forces acting on the frame at all, so it must be a pure vertical force. So with that in mind, you can take moments immediately about any point other than B. Let's pick C. And find that R times 1, so fingers on C, R times 1, upward force times 1, upward because that's the closest arrow to B, which would be a clockwise moment, is equal to the 1,000 times 9.81, which is the magnitude here, times the full 3 meters back to C. And that's going to allow you to find R at 29,430 newtons. So that is the force at the hinge pin. That is the force that this hinge pin is experiencing. Next is to find the force in member AD, which is this one here, which is going to require us to make that cut, that imaginary cut. So here is the imaginary cut. I'm choosing to work with the left-hand portion, leaving it exposed under the influence of 1, 2, 3 forces. I'm going to take moments about B, which is down here, thereby eliminating whatever this force is, which is going to leave me with a very simple matter of force AD times 1 as a clockwise moment about B. Let's see why that is. This force AD times the meter back to B, because it's conveniently 90 degrees here. So you don't even have to take components. You can just immediately take the full force AD and multiply it by 1 meter and use that as the clockwise moment about B. And that's equal to the only other moment, which is an anti-clockwise moment at 1,000 times 9.81, that's this one here, times the full 2 meters back to B. And that will allow you to find the force in member AD at 19,620 newtons.